Hi there, Karnika here, and today we're going to explore the evaluation of machine learning models. We'll learn how to assess their ability to predict on unseen data, covering both foundational principles and advanced techniques to ensure robust models. Before we start, it is important to note that there is no one-size-fits-all approach to evaluating machine learning models. The choice of metrics depends on factors like problem type, dataset characteristics, and a specific goal. For instance, grading competition often have their own preset evaluation methods outlined on the competition page. To score higher on the leaderboards, your model must excel according to those specific criteria. In this video, we'll discuss some of the common evaluation metrics used in machine learning. So why do we need to evaluate? The core objective here is to determine how effectively our learning algorithm performs, especially on unseen data. Imagine it like preparing for a surprise test, and we want our model to handle any situation. Let's understand the foundation, training, and test set. To build a reliable model, we split our data into two parts. Training set, used to teach the model patterns, while test set, used to evaluate its performance on the unseen data. This prevents overfitting, where the model performs exceptionally well on data that it is trained on but struggles with new data. Typically, we split our data into a ratio of 80 to 20, allocating 80 for training and 20 for test. However, this proportion can vary based on factors like data set size and complexity. By separating data into training set and test set, we ensure our model can generalize well on new data. This is a crucial step before applying evaluation metrics. We use various metrics to assess the different aspects of model performance. Let's explore some common ones over here. Error metrics. Error metrics quantify the difference between the predicted and actual value. In regression, we use mean absolute error and mean square error to understand the average error. Mean absolute error calculates the average of absolute difference between the predicted and actual value, whereas mean square error calculates the average of square differences between the predicted and the actual values. Let's have a look at the code. To calculate mean absolute error and mean square error, we use Python's Scikit-Learn library. By using the built-in functions in Scikit-Learn library, here's how we can do it with a sample data. Accuracy is a pretty straightforward metric that gives us the percentage of correct prediction. Accuracy is the ratio of correctly predicted value out of the total number of predictions expressed in percentage. In the code, we can calculate accuracy using Python. Again, using Scikit-Learn library, there's a single built-in function that simply performs the calculation on sample data. Next is precision and recall. Precision and recall are crucial for classification, especially with imbalanced data set. That is, when one class is more abundant than others. Precision tells us how many positive predictions were actually positive, while recall shows us how many actual positives were correctly predicted. Precision is the ratio of true positives to the sum of true positive and false positive, whereas recall is the ratio of true positive to the sum of true positive and false negative. To calculate precision and recall, we again use the Python Scikit-Learn library and call the built-in functions. Misclassification. Misclassification rate complements accuracy. By showing the proportion of inaccurate prediction, misclassification rate is the ratio of incorrectly predicted values out of the total number of predictions, expressed in percentage. Again, here's the code to calculate misclassification rate using Python. We simply derive it from the accuracy score. Here's how you can do it on sample data. Next is confusion metrics. Confusion metrics is essential for classification models. It provides a detailed breakdown of the model's performance by category, showing how many instances were correctly classified: true positives, true negative, incorrectly classified, false positives, and false negatives. To calculate confusion metrics, we use the confusion metric function from Scikit-Learn. We provide the actual and the predicted values as input, and the function returns a metric representation of the distribution of correct and incorrect predictions. We plot a heat map for visual speed and clarity. Lastly, cross-validation. To get a more robust estimate of models' performance and to reduce the impact of random data split, we use cross-validation. A single test being split can be misleading. Cross-validation helps addressing this by dividing the data into multiple folds. Each fold takes turn being the test set, while remaining folds serve as the training set. By leveraging the result across these folds, we obtain a more reliable estimate of the model's ability to generalize. There are several types of cross-validations. K-fold cross-validation. This is the most common method. The data is divided into K equal size fold, and model is trained on K-1 fold, tested on remaining fold. This process repeats over K times, and each fold serves as the test set once. Next is stratified K-fold cross-validation. This is used when the target variable has imbalanced classes to ensure that each fold maintains the same class distribution as the original set. Next is leave-one-out cross-validation. In this method, each data point is used as the test set, for remaining data points are used as the training set. So it's computationally very expensive, but can provide good estimate of the model's performance. Here's how the code performs cross-validation in Python. Cross-validation utilizes cross-val score function from Scikit-Learn, and here we split the data into 3 different folds. So we're setting the CV value is equals to 3 and train the model, which is a logistic regression model, classification model, specifically on each fold, using the remaining folds for testing. This process is repeated for all the folds, and the average score across all the folds provides a more robust estimate of the model's generalizability. Okay, so we have explored machine learning evaluation from understanding its goal to matrix and using cross-validation. These techniques are essential for refining and ensuring a robust model that can perform well on unseen data. Thank you for joining me in this video. I'll see you in the next one.